I was covering transparency and opacity. I gave 5 mechanisms. I'll review them very quickly. Okay, and here we have 5 mechanisms, variables that you should keep in mind when you look at things that are transparent or opaque. You're going to try to answer the question of why is something opaque, why is something transparent. And the first criteria, or the first variable, the first thing you have to keep in mind when you do analysis is alignment. And we showed that with polarization. You can shine a laser through 2 polarizing lenses, as we show there on the upper right, upper left. And when you turn that at 90 degrees, one of the lenses with respect to the other, it blocks the light. You don't see the light at the at the screen, the black screen. Okay, there you see it, and as soon as we turn it, you don't. Okay, so transparency, apparently, according to Mother Nature, has some, or alignment has something to do with transparency. In some instances, doesn't mean in all. We're giving you different clues here how Mother Nature does transparency and opacity. Another one is quantity. Right at the bottom, you'll see there. Okay, if we put many sheets of this plastic thing, you can't see the candle, the light on the candle. If, on the other hand, you put just 1 sheet, you can see a lot more. So the quantity of sheets also has a bearing on transparency and opacity. Now, one fella, I'll stop here with this, talks about, for the 4th time, I think, talks about this. Talks about the, let me get back in here. Talks about two-way mirror. He says a two-way mirror is half silvered. How it acts has nothing to do with molecular structure of the glass. Yeah, nobody said it does. Again, I don't know if this fellow went to high school or what, but in high school you learn that a molecule is not the same thing as an atom. And an atom is what quantum mechanics works with. Atom and below, usually. Okay, that's the realm of quantum. They want to know what's happening in that invisible subatomic world. Okay, and I mentioned that now 3 times, so I hope this guy's paying attention. Anyways, we're not talking about molecules. We're talking about the atoms. We're talking about the atomic level. Okay, and it has nothing to do with glass coating, and it has nothing to do with lighting in the room. The question that we have before us has nothing to do with those two. Okay, one more time, because this is, I think, the 3rd or 4th time that I mentioned this. The question before us has nothing to do with whether the glass has coating or not. The question before us has nothing to do with lighting in the room when you have these one-way mirrors. From one direction, you see a mirror. From the other direction, you see a glass. The person that sees a mirror does not see the person behind the glass. And the person who sees a glass sees the person seeing himself in the mirror. Okay? Now people say, well, the coating, well, the lighting in the room. The question before you has nothing to do with either one of those variables. Okay? The question before you has nothing to do with whether there's lighting in the room or whether there's coating on the one-way mirror. Okay? And so what are we talking about? What's the situation? What is the question? Okay, here's the question. Quantum mechanics, okay, provides no physical interpretation for transparency or opacity. What they give you is the following. They say there's a photon, which is that little red ball, okay, that comes and hits an electron ball, okay, and because the electron ball absorbs the energy, the photon, the whatever you want to call that little ball, a wave packet, because it absorbs the energy of that little photon ball, it jumps to a higher energy level. If it does so, if it absorbs that photon, the material is opaque. In other words, the photon does not go through and reach your eye because it was absorbed by the electron. This is the explanation that quantum mechanics gives us. Let me repeat, okay, one more time. We have this electron at different energy levels around the nucleus of the atom. A photon comes in, it delivers its energy to the electron. If it's sufficient energy to knock the electron from one energy level to a higher energy level, the photon is absorbed, and therefore the photon does not go through to your eye, and the material is opaque. If instead the electron absorbs the photon and spits it back out, or doesn't absorb it at all because the photon does not have enough energy to knock the electron to a higher energy level, then the material is transparent. Okay, we got that? So it's got to do with atoms and not with molecules, and it's got to do with whether the photon has enough energy to knock that electron to a higher energy level. That's the explanation. Now, what's the problem with that? Well, the first problem is that, there are no such things as particles in quantum mechanics. The famous particle is not a particle. particle is a misleading word, very misleading, because what they're talking about is point particles, meaning point nothings, because they're really talking about a concept known as the wave function collapse. So what they're moving there, those yellow balls that you see moving there under the word particles, those are wave function collapses. What you're staring at is a bunch of numbers really that are flowing. And they represent those numbers with little balls, supposedly representing locations. And locations of what? Well, it's just locations. You have no physical object in any of those locations. Okay, so that's the first problem. And they also use the wave whenever they run into trouble. There's no such thing as a wave first in the standard model of quantum mechanics. And then we have a separate problem, or a more fundamental problem, which is the fact that those blue and red arrows, those are vectors. They have magnitude and direction, and what the mathematicians have done, they set them in motion. So what you're staring at is the flow of vectors, the flow of magnitude and direction. What is magnitude? It's a number. What you're seeing is a flowing of number 5s and 6s. So we don't have a physical interpretation to what quantum mechanics offers for transparency or opacity, because there is no physical object. That's why. Okay, so that's where we start. But the mechanism that that quantum mechanics proposes is the one you see at the top. Photon comes in, knocks the electron to a higher energy level. In that case, the material is opaque. And if it doesn't have the energy to do that, if the photon cannot knock that electron to a higher energy level, the material is transparent. The photon goes through and reaches your eye. Okay. So what's the problem with this? With just the explanation, assuming we concede the particles. Okay. Well, here's the problem. Okay, the problem is that we have this one-way mirror, okay, and the man on the upper left there, he looks at the mirror, he sees himself. He doesn't see the lady who's on the other side of the mirror. The lady looks and she sees right through the mirror, because she's looking actually through a glass, and she sees the man. So the man sees himself in a mirror, whereas the woman sees the man. So now we perform a little experiment, and what we do, we take two lasers, okay, we take the lasers and put them on each side of that mirror. On the one hand, we have the laser on the man's side, and that just reflects the light back to you. You see a little dot on the mirror, and that's all you see. On the other hand, the lady, she sees the man's dot, the man's laser come to her eye, and if she points her laser, it hits a brick wall. Okay, so the light from the man, the laser light, goes through and is seen by the woman, but the light that the woman sends is not seen by the man. Okay, that's the issue. Now, has the mirror changed in any way? We have the same mirror in either direction, the same material. Okay, this is not an issue of molecules again. This is an issue of atoms. Remember what was the mechanism? That the photon from the lasers is absorbed by the electrons that form the mirror. Okay, and in either direction, we have the same material. Okay, so the photon should be absorbed from the laser, should be absorbed by the electrons in the mirror in either direction. But it's not. It's only one way. And that's what you have to answer. So here it is in more detail, okay? And so the question is, here we have the laser that comes from the left, okay, from the man. That one goes through. It goes through the atom. We only put one atom just so that people have it very simple, okay? That green arrow just goes through. Whereas the one from the absorbed side, that one is absorbed by the same atom, by the same electron. And so the question is why? Why does the energy, the photon, whatever you want to call it, go through from left to right and does not go through from right to left? This is the question you have to answer. Okay, and so it's got nothing to do with the lighting in the room. It's got nothing to do with the coating on the mirror, because the material is the same in either direction. Okay, the photon should be absorbed by one atom. We're just going to look at one atom in that mirror. And that atom in that mirror should absorb in either direction. Why does that atom only absorb in one direction and not in the other? That's what you got to answer. If you don't have an answer for that, then you simply are eluding the question. Okay? So I rest my case on that. If a person wants to answer, he can answer. Otherwise, he's got to run with his tail between his legs like he has now for 3 sessions. Okay, another fellow raises issues here related to this, is those empirical demos of alignment, quantity, temperature, stiffness of frequency are extra scientific, as you always said. Well, again, I point with my finger at the moon, the guy's staring at my finger instead of looking at the moon. He's confusing experiments with the mechanisms I'm providing for how Mother Nature does opacity and transparency. Okay, I'm looking at the variables. See if this centers his head. I'm looking at the variables that Mother Nature is using under different circumstances. You have to figure out which ones of these she uses for glass, which one she uses for water, which one she uses for air to produce transparency in those materials, and which one she uses to produce opacity like, a brick wall. How does she do this? Well, I'm giving you the clues, the things. It's not that we're running an experiment. But see, again, I point to the moon, they're staring at my finger. This is not about experiments. This has to do with the mechanisms that give you an idea, okay, how Mother Nature could be doing transparency and opacity. And these are the variables, the things that you got to look at and the things you have to consider if you're going to answer the question. And I doubt very much this gentleman can answer that question anyways, because if he's still staring at my finger. Okay, so continuing here, we have temperature on the upper side, but see, all these three on the right-hand side are kind of related because stiffness is a function of temperature, and temperature is a function of frequency, okay? And so all these three are kind of related, but it gives you an idea what to look for, again, for transparency and opacity. In the case of temperature, I showed the case where glass full of water is frozen, and when it's frozen, you can't see the pen. It's only when the glass is melted the ice is melted that you can see right through and see the pen through the water. So there's a difference between the water being cold and the water being in liquid state. But one fellow pointed out that what you're doing is freezing a lot of oxygen molecules. Irrelevant, really, because the point here is that even in the case of oxygen, oxygen when it's frozen, it becomes invisible, not invisible, but there's a tendency for it to become opaque. And then I showed the opposite with argon, showing that when you have argon in a solid and liquid state, it tends to be transparent, whereas when it's in a gaseous state, primarily in a plasma state, well, at that point it gets violet. And so it's opaque. So it's in reverse for argon. And so what you got to do is look at temperature as a factor that affects opacity and transparency. That's against what we're trying to do here. We're trying to show you all the things to keep in mind. Another one is stiffness, which is again related to temperature, and you have a solid crystal structure like you see there in a center, and you have the other one, which is a gaseous state, could be air or whatever, and again, it tends to be more transparent the less stiff it is in general. Okay, so stiffness is one of the criteria you have to think about when you're looking at transparency and opacity. And the last one we covered was frequency, and you can't do that with waves because, again, there's no physical object called wave, okay? And we replaced that with a rope, and with a rope, yes, you can talk about, the lengths. And what we held is that the longer the link, the colder it is, meaning now we go to temperature up at the top, and the stiffer it is, and we go down the middle there, okay? So if you make the links longer, you have a colder rope or colder material. Vibrates less, it gets stiff, and the stiffer it is, it tends to be opaque, and vice versa. The hotter it is, the shorter the links, the more energy you could say in terms of mathematics, the higher the frequency, and so what happens is now it tends to be more transparent. Okay, so that's a summary of what we covered. Okay, these are things for you to look at and figure out which ones of these variables, these factors, affect transparency and opacity when you're analyzing, transparency of air, water, glass, etc. Okay, but today we're going to add a couple more, and it's going to be this one, distance and speed. And the question is, does speed affect transparency or opacity? The fact that something is very far away, like a glass, if it's close by to your nose, is it more transparent than if that same glass were farther away? See, in one case, if you have it close to your face, you can see through that glass. You're not paying attention to the glass. You're paying attention to the tree that you're staring at. It's like the glass does not exist. But as you separate the glass and put it farther away from your face, closer to the tree, for example, does that the fact that that glass is now distant from your eye, does that affect the opacity of your ability to see through the glass? I mean, now you have distance between your eye and the glass. Okay, that's what I'm suggesting here. And so let's start at the beginning here with this. And here it is. You see a curve, light versus distance. And you can see that light tends to become, the intensity of light tends to reduce the farther the light is. And this has to do with what do they call the inverse square law. This light intensity falls off as the inverse square of the distance. They call it a law. So intensity falls off. And so the question is, does this have anything at all to do with transparency and opacity? Okay, and again, it's for you to ponder these questions to see if it's worth including within the variables that you're going to factor into your analysis of transparent material. And here, let me give you a for instance of something you may want to look at. Okay, and here you have 3 pictures, and I want you to look at the little sign there, the chevron sign in red that I've circled in red. Well, you can't read the letters there. Okay, you're looking through the windshield of a car, okay, and you're approaching. You can't see the letters there. You can barely see the sign. Okay, well, what happens when you come near? Well, it suddenly becomes a little more visible. Okay, you can see better now. And again, it has to do a little bit with the distance, right? Does it have anything to do with the glass that you're staring through? And the nearer you get a little near. Now you can see the letters of the chevron sign, okay? So did distance make a change? And you would say, yeah, I made the change as far as seeing the sign. Does that mean it had anything to do with the windshield itself, which is the material we're analyzing here, right? We're analyzing whether the windshield has, transparency of the windshield has something to do with distance, okay? And let me show you something else that you probably missed by looking at these pictures, and that's this. Here you can see that the sky was bluer when it was closer to you than when it was farther away. In other words, as you move in that direction, what you're seeing is that the sky is becoming bluer. And is that because there's this overhang bridge that you're going through? Is that why that's that case? Or has it to do with the windshield itself? Okay. And you can see other things in that picture, like, for example, that tree that's close to the chevron sign. You can barely see it. It's kind of nebulous in the upper picture, but as you get closer, you can see it more vividly. Okay. And again, is this a question of, does this have anything to do with the windshield at all, or does it have to do simply with the distance from your eye to the thing that you're observing through the windshield? Okay. Factors, again, to consider. Okay. All I'm throwing in there is all these factors so that you ponder if they have anything at all to do with transparency or opacity. Okay, let's look at speed. Okay. Speed of light is known to be little c. According to Einstein, according to me too, light is a constant. Light travels always at little c, at 300,000 kilometers per second. Now, that's not exactly what Einstein's disciple believe today. They believe that light changes speed depending on the medium it goes through, because they think it goes through things. Okay? So the way they look at it, the more opaque an object is, the slower that the little photon ball, or whatever that photon thing is, goes through it. Okay? And here we have the famous case of the prism. We have white light coming in, it hits the prism, and it breaks down into different colors coming out at the other side. And so the question is, how does Mother Nature do that magic trick? Well, the way it's explained today is that light travels slower when it comes out, because it's like if it hit a brick wall. Again, it's the stiffness, you can say the crystal structure of this material, such that, light hits, you have these little balls, ping pong balls. You're supposed to think of them as such, like little balls, because that's what they illustrate. And these little balls hit the side of the prism, go through the material, refract, right? And then come out at the other side, also in a refractive angle. But they don't come out as a white light. They come out broken up into different colors. Okay, and so the question is, how does Mother Nature do that trick? This is a transparent material. It's translucent. We're always going to use the word transparent, okay? It's transparent. It allows light to go through. And so does light go through? Is it a little ball that's going through the whole material and coming out the other end? And if it comes out the other end, okay, we can understand it's coming out slower because it hit a material which has a solid crystal structure, so it slows it down. Let's concede that, okay? Now, does light travel at a different speed coming out? Does red color coming out or blue color coming out do they have different speeds? Does red light travel slower than blue light, slower than white light? Or do they all travel at the same speed with that conversion factor that you see there, where frequency exchanges for wavelength? Now we can do that with a rope, very simple. I've shown this many times. Links are very small when it's very tight, and when you unwind, you have longer links and fewer links. That's what that equation says. How do you do that with particles? How do you explain that with waves? Why doesn't a wave get bigger, longer, and also have more waves passing through a given point? Speed of light, right? We're changing the speed of light. We're saying that light travels faster or slower, right? Tachyons travel faster, horse travels slower, whatever. Or ocean wave travels slower, right? So the question is, you can't explain this transparency with particles and waves until first you identify the physical object that is doing the waving. In the case of particles, there's nothing to explain because it's zero-dimensional particle, point particle. It's not even a particle. It's a concept which they turned into a particle or represent with a particle. So the particle is dead. Quantum mechanics has no explanation with particles because they don't have a particle to begin with, a corpuscle. Waves again, there's no physical object called wave, so we can't explain it with wave. But assuming we did explain it with waves, why doesn't the wave travel faster or slower, right? And why doesn't the wave, also get longer or shorter? Because if the wave can get longer and travel at the same speed, then it's traveling faster than light, okay? Because now if you multiply longer wavelength time, the same frequency, right? Then you get a faster speed of light. And vice versa. If you increase the frequency and leave the wavelength alone, you also get a faster speed of light. And if you increase both frequency and wavelength, I don't see any reason why you can't increase both, right? Why would you not be able to increase both the frequency and the wavelength? Okay, you increase the wavelength, and passing through a given point, it passes, at a faster frequency. Why can't you do that? You can't even do that with a particle. You can increase both the frequency and the wavelength, you got a faster speed of light. And so why can't we do that? Why can't we travel faster than light? And for some reason, Einstein said, the speed of light, at least in a vacuum, is constant. You can't change it. And so what they did, they created for materials what is known as refractive index, a conversion table that has to do with opacity, with how whatever material there is there slows light down. And if that's the case, if it slows light down and we get colors coming out the other end, do those colors of light, the red light, the blue light, whatever comes out, green light, do they travel at different speeds? Or do we have the same speed of light coming out? And if so, because there's another question, if light had to go through the prism and it was slowed down by the prism, what accelerated light when it came out to the point where now it travels again at the speed of light? Like if we had that prism in outer space, right? We shine a light on the prism, we have vacuum and vacuum on the outside of the prism. The light travels slower through the prism. Let's concede that. Okay, so it travels slower. What speeds it back up when it comes out back into space? Why does it travel back at little c, 300,000 kilometers per second, once it comes out the other side of the prism? Okay, so all these questions have to be answered. With a rope, no problem. You have a white light, which is a whole bunch of ropes, right? It's a menagerie of many ropes coming into the prism. And when they go from one atom to another atom to another atom, the relay process, well, they don't lose speed. What they change is frequency in exchange for wavelength. And when they come out, because they can't come out from different atoms that are coming out, well, then it's not that each one travels slower or faster. They always travel at little c, even through the prism. It's always, like always, no matter what material in the universe, it always travels at little c between any two atoms. The only thing that changes is the wavelength in exchange for the frequency. And so when the wavelength is longer, you have smaller frequency, meaning fewer links on the rope. And when the links are shorter, you have more links, greater frequency. Very straightforward, simple, we're done. We have an explanation for transparency through a prism, okay? And here's something that kind of reinforces that, okay? It's the Harvard Tower experiment. Two fellows, Pound and Rebka, in 1959, I think it was. What they did was they went in there and they threw a laser. I'm not sure if it was a laser, but they did send a high frequency light. That's what it was. High frequency light, and I think they sent it downwards from the top of the tower, Harvard Tower, down to the basement where the detector was. And what happened was they realized that the frequency increased, okay? Meaning that the wavelength got what? Shorter, right? And vice versa. If you reverse the experiments and send the beam upwards, okay, to the Harvard Tower, you would receive the opposite. You would see that maybe you have gamma ray coming out or whatever high frequency signal you send out. And as it gets to the top of the tower, you're going to measure it at a longer wavelength and lower frequency. Well, what you've just described is a rope, because when you take a rope and you tie it in, I don't know, to a telephone post, and you stretch it out as long as you want to the end of the street, you'll see that the links closer to the telephone post are shorter. And as the rope is extended all the way out, the links become longer and you have fewer links. Okay, and that's what I'm trying to show there. That's in general the case, and that's, I think, what the tower experiment, the Harvard Tower experiment showed. Okay, that as light attempts to leave the Earth, okay, and the same thing would apply to the sun, by the way. Any light coming out, any rope coming out of the sun, extending out from the sun, as it extends outwards to another star system, to another galaxy, the links get longer as we move outwards from whatever, in this case, the sun or the Earth, it wouldn't matter what. So the links should get longer, okay? And here, that's the theory, okay, for you to ponder. And here, let me show you a little graph that puts that into the right perspective. Okay, here you have the sun, and what you have is gamma rays coming out of the sun, very high frequency rays, okay, short wavelength, lengths in the case of the rope. And only as you move out do the links get longer, okay? So a rope that starts in an atom of the sun, that ends in an atom of the Earth, would not have enough length, that whole rope would not have enough length to have such long links as one that, for example, like the one on the top, extends to another star or another galaxy. If that atom is connected to an atom in another galaxy, the links will become longer only much further out. And the suggestion here is that the gamma rays that we receive here on Earth from the sun are not of atoms that are connected to atoms of the Earth. Okay, they are atoms that are very far away, and those gamma rays just come through the Earth and continue going all the way to whatever object that rope is tied to. Okay, so this is the theory I'm proposing. Maybe someone has a better idea, but this is what I think is happening out there. I think that the gamma rays that reach the Earth are not atoms that are, the rope does not end in an atom that is part of the Earth. Okay, that's my 5 cents worth on that. Okay, okay. Let me just show you some of the conclusions. Okay, does distance affect opacity transparency for visible light? In other words, comes to your eyes. Okay, so I'm not telling you, I'm asking you. Okay, and is it the same to see through a window that is nearby, like tied to your eyes when you see the tree through that window? The same thing as if that window were close to the tree far away and you're looking through that window at the tree. Okay, is there a difference that does the distance affect the opacity of the material through which visible light comes through? Okay. You can even shine a laser, try it with a laser and have someone close to the tree or some kind of screen there to tell you whether the laser is the same size or the same intensity as it was when you had the glass close to the laser. Okay, that's an experiment anyone can do, okay, and more or less get an idea of how to answer that question. Okay, and then the speed of light is constant. Always travels at little c. Never changes its speed no matter what. Why? Because it's a rope. So all it does is change its frequency for wavelength, wavelength for frequency. Higher the frequency, lower the wavelength. In other words, the link length, the length of a link. And the shorter the link, the more links, frequency, that you get. Very simple, very straightforward. C equals frequency times wavelength is the equation of a rope. There is no other object you can imagine that can simulate that equation. It's got to be a rope. And it's been confirmed little c is 300,000 kilometers per second, and more or less, rounding off. And it is a constant, at least they claim it's a constant in vacuum. Very little difference with air, even though there is a slight difference. according to quantum mechanics, in speed. Okay, I'm saying the speed is the same. It's just that one atom is relaying to another atom through there, and there's refraction and all kinds of good stuff in there as well. Okay, prism is transparent. We can call it translucent. I use the word transparent so to keep it simple. And prism does not change speed of light. Okay, what we have is one atom connected to another. It's relaying the signal it receives at the speed of light from one atom to another. So it's a relay race. Okay, and what you're relaying is torsion, a signal that you receive. And prism exchanges frequency, number of links, for link length. Okay, and again, quantum mechanics has no answer to these questions because quantum mechanics does not have a physical object to begin with. Whether particles or waves, whichever one it uses, there is no physical object yet in front of us.